Hey y'all, today we're going to look at our second periodic table trend. Today we're going to look at ionization energy. We're going to start with a quick recap of Coulomb's law again. And then what we're going to do is jump into how we can use Coulomb's law to predict the trend of ionization energy. Let's go ahead and get started. Let's start with just a basic definition of ionization energy. Ionization energy is the removal of an electron from the gaseous state of an atom. So you got an atom all by itself. It's in its gaseous state. How much energy does it take to rip away one electron from the valence shell? That's ionization energy. As with any periodic table trend, ionization energy is going to be predicated on Coulomb's law. Coulomb's law, which in the case of a single atom is going to be the effective nuclear charge on top divided by the number of shells or energy levels on the bottom. Okay, so remember, as the effective nuclear charge goes up, the Coulombic attraction also goes up. As the number of energy levels increases, so the number of shells increases, the force of attraction is going to go down. Okay, so going back to that basic trend. But the thing about ionization energy is there's some nuance because it doesn't always follow the trends we'd predict. So what we're going to do is we're going to talk big picture trends and then start talking about maybe some of those exceptions and nuance as to why ionization energy might not be exactly what you'd think just based off Coulomb's law. So one more quick look at the periodic table here. From left to right across a period, effective nuclear charge goes up. As effective nuclear charge goes up, the periodic table trend is that of increasing Coulombic attraction. Okay, so that's going to increase the force it takes to rip away that first ion or that first electron. As we go top to bottom down a group, remember, you're adding number of energy levels. The more energy levels there are, the further those electrons, those valence electrons, are going to be from the nucleus. That is going to cause the relative ionization energy to decrease. So if we want to just look at a periodic table based off of direction, as you go up and to the right, your ionization energy is going to increase. As you go down and to the left, your ionization energy is going to decrease. But as I said, there's some nuance. Take a look at this graph. This graph shows ionization energy of different elements as you go up and around and down the periodic table. So let's take a look at these real quick. The first thing that you're going to notice is that going from the first atom, hydrogen, to the second atom, helium, there is a significant increase in ionization energy. Now that makes sense. The effective nuclear charge of helium is 2. The effective nuclear charge of hydrogen is 1. They have the same number of energy levels, so it makes sense that it takes more energy to remove that first electron from helium than it does from hydrogen. Then we go to the next element. That next element is lithium. Lithium has a very low first ionization energy. The reason lithium's is low is because now we go back to the same effective nuclear charge as hydrogen, but we've added an energy level, 1 shell beyond what hydrogen had. And as a result, lithium's effective nuclear charge being the same and the number of energy levels being greater means that its ionization energy is going to be less. That trend continues for beryllium, Be. Greater ionization energy than with the lithium. And the reason is because, again, you increase the number of the effective nuclear charge from 1 to 2, and it's in the same number of energy levels. Beryllium and lithium both have 2 energy levels, 2 shells. But then we get somewhere weird. Notice how boron, B, actually has a lower first ionization energy than beryllium. That's odd. With boron, the reason for this exception, the reason its energy is lower than you would have predicted, is because that 1 electron you're removing from boron is the first in the next energy level, that 2p energy level. And by removing that 1, you get to a full 1s energy level or 2s energy level. So you have a full 2s energy level. And that's a little bit more stable because of the lack of electron repulsions. So remember, the reason for these exceptions is because of increased electron repulsions. You don't need to necessarily know the nuance of it all, but you do need to be able to predict where those exceptions might be. So let me tell you. The first exception is when you're losing an electron to get to a full sublevel. This is going to be the case with things like boron and aluminum. So with boron and aluminum, We're losing an electron to go back to a full sublevel. The second exception, which you're going to see in the elements oxygen and sulfur, is that they're a little bit lower because their removal gets you back to a half-filled sublevel. And a half-filled sublevel is a little bit more stable than a sublevel that has 2 electrons within an orbital. Okay, so a half-filled sublevel, each orbital is filled with only 1 electron, not 2. So again, this is all about electron-electron repulsions. Okay, these are the exceptions. So keep in mind, when it comes to exceptions, the reason is always because of increased repulsions between the electrons. If the ionization energy is less than you'd expect, it's because you're taking from a position where there's more repulsions and going to a position where there's less repulsions than there would have been otherwise. So if you look at these exceptions that I've circled here, what you can see is that they might not be all over the place, but where they do happen, they happen regularly. So you can see going from the boron back to beryllium, going from the oxygen back to nitrogen, and then all down the periodic table in those positions, you will see these same exceptions over and over and over again. Remember, down a group, we share chemical similarities. Ionization energy is one of those chemical similarities that is shared. When it comes to these exceptions, you look at the electron configurations here and you can see the same thing. When you're removing an electron from the boron to go back to beryllium, we're removing it from the 2p sublevel. When we remove an electron from aluminum, it's coming from the 3p sublevel. And as we go back, we're now returning to a full S sublevel. That's going to take a little bit less energy because that full 2s sublevel is a little bit more stable than it would have been otherwise. Similarly, with nitrogen to oxygen or phosphorus to sulfur, what we're doing is we're going from a position where we have 2p4 and going back to 2p3 in the case of nitrogen and oxygen. What that does is it makes your orbital diagram, again, 3 electrons, all with the same spin in separate orbitals. That's pretty stable, relatively speaking. The final concept we're going to talk about is what happens when you don't just remove 1 electron. What if you remove 2, 3, 4, or even more? The reality is, as you remove every electron, the atoms are going to get smaller. The reason they're going to get smaller is because you have fewer electron repulsions going on when you remove more electrons. So after the first ionization energy, all those other electrons are going to get a little bit tighter. After the second one, a little bit tighter. What that's going to do is it's going to increase the relative Coulombic attraction of the nucleus on the remaining electrons. That's going to make the second ionization energy higher than the first. The third is going to be higher than the second, and the fourth is going to be higher than the third. But within this, there could be some pretty dramatic shifts too. For instance, what if you go from 1 electron and then you go back and the next electron's a full energy level below it? So when we look at lithium, taking that first electron might be easy, but that second electron is isoelectric with helium. That's a full energy level lower. That's going to be an incredible jump in the ionization energy as a result of dropping down an energy level. What's cool about this is it actually allows us to identify atoms based on their ionization energy trends alone. Each time you go down from 1 energy level or 1 shell to the next one below it, what you're doing is you're jumping the ionization energy. So what you're going to do is look for this big jump, and that'll tell you which electron was the first to be removed from that lower energy level. So for lithium, the second ionization energy is going to show that great jump. What about magnesium? Well, in magnesium, it's going to lose its first 2 electrons with some ease. The second one's going to be higher than the first, but not by a ton. But then you drop another energy level. And so removing the third electron for magnesium is going to take the most energy. So what you're going to see is like an increase between first energy, second energy, but then a big increase between the second energy and the third energy. And that's going to really tell you what the charge of the ion is going to be. And we can actually use it to identify the ion. Let's jump in with a practice problem. And in this one, I'm kind of wrapping in a few different things together. So what I want you to do is compare the first ionization energies of aluminum, Al, thallium, Tl, and barium, Ba. Which would you predict to have the highest first ionization energy? Then I want to add in one more. Let's include the third ionization energy of aluminum, just to see if you can do that. So we got 4 things to compare. First ionization energy for aluminum, third ionization energy for aluminum, the ionization energy for thallium, and the ionization energy for barium. So what's the rank? Well, the first thing to keep in mind is that barium is going to have the lowest effective nuclear charge here, +2, and the most number of energy levels. As a result, it is going to have the weakest ionization energy, or the lowest ionization energy of all this group. The next one is going to be thallium. Thallium, because it has the same number of the energy levels as the barium, but it has a much higher effective nuclear charge. So it is going to have a greater first ionization energy than barium, but because it has more energy levels than aluminum, it is going to be lower than aluminum. Aluminum, which has the same effective nuclear charge as thallium, but has way fewer energy levels, is going to have a greater first ionization energy than the thallium will. And then finally, remember, as you continue to pull more and more electrons away, the ionization energy of each successive electron is going to get greater. The third ionization energy of aluminum is greater than the first ionization energy of aluminum. Therefore, it will be the greatest. Second practice problem here, and this again is going to be more of the AP level problem. All right. When I say an AP level problem, it just brings in a few other components that you need to understand. So take a look at these 4 successive ionization energies from the same atom. And with this, predict which group on the periodic table that element came from. Take a second, look at it. What do you think? So do you notice how the first 2 ionization energies, it goes a little bit bigger from 1 to 2, but then from the second to the third, it goes up by a lot? That's indicative of the fact that we've gone from removing a valence electron to removing a core electron. Okay, so we've dropped down in energy level. That tells me that this atom is going to have had 2 valence electrons in its original ground state, its original atomic form. So 2 relatively easy to lose electrons, followed by 1 that's really hard. That means that this was an alkaline earth metal. And as an alkaline earth metal, keep in mind that it is going to be in group 2 on the periodic table. So this atom, wherever it came from, is definitely in column 2. So that wraps up today's video. Today we learned about ionization energy and how to predict it, some of the exceptions for it, and also how to use ionization energies to actually predict what atom we're even looking at. Today's video was written, produced, filmed, and edited by Ava Ng and Claire Peng. I'd like to thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.